Hello again. So yesterday we looked at what would happen if we had, say, 3.5 moles of H2, and we wanted to know how many moles of oxygen that was going to use up. And we said we're going to use our good old friend dimensional analysis, right? And I couldn't get the happy faces in because I was typing on my Chromebook. So, happy face here, moles. And what we're going to use are called molar ratios. Okay. Molar ratios are ratios of moles, I know, right? That we're going to get from a balanced chemical reaction. Okay, now this reaction is balanced for you. Pretty sure. Yeah. Okay, so we have this balanced chemical reaction, and we're going to get the ratio of moles out of that. So I know I've got moles of H2. Now the same rules that have always applied will apply here too. Whatever's here goes here, and whatever's here is going to go here. The one rule that doesn't apply this time is when we say that there's always a 1 in front of the moles. There's not always going to be a 1 in front of the moles, but there will always be a whole number. So I've got moles of H2 here. Whatever's here goes here. We're going to put the moles of H2 down here, and I'm going to pull that coefficient off my balanced chemical reaction. I have 2 moles of H2, and then I'm going to put where I'm going up here. Now, I didn't write it down, but remember I said we're going to go to moles of O2. So I've got 1 mole O2. This is where I'm trying to get. Okay, right, there's a 1 here. There's a 1 there. That's how I'm getting this number. This is where I'm trying to get. So I'm done. Equals 3.5 divided by 2 is 1.75 moles O2. Right? And this is all well and good, but like we've talked about before, you can't measure moles in a lab. This isn't practical, so we need to put it into terms of something that is practical, which brings into play our good old friend, the molar road. You guys remember this thing? Of course you remember this thing. You know you do. So we have this molar road. Yay, molar road! But it only gets us, say, from, and it doesn't quite fit my frame here, particles and mass and volume to moles, and maybe moles is something else. This one always kind of bothered us. We weren't really sure what to do with it, how this formula came into play, right, where this was. What I was doing, setting you up for our brand new, improved, better molar road, yay! You're like, oh God, it's got 2, and why does it have an avenue? Okay, I'm gonna move my camera here just a little bit. Back it out so you can see. Okay, so this is our new and improved molar road. It has a molar road and molar avenue. We can go from one substance to another, and that's the separation between molar road here and molar avenue. It takes us from moles of one thing to moles of another using our good new friend, molar ratio. Okay, but the process really works exactly the same. If you liked molar road, now you've got this new and improved one. This is in the classroom. This is, I believe I put it in a reference folder as well as attached it to this lesson. If you liked the molar road, if you liked to drive from one point to another, see what conversion factor you needed, this works great. If you were happy with the whatever's here goes here dance, it's going to work just fine too. Let's see if I can get my camera balanced back up here. Okay. So what does that mean for us? So now the new question is going to read something more like, if 12.3 grams of H2 react, what mass O2 is needed? Question mark. Okay. But the process is exactly the same. Okay. And that's why I call these comfort bars, why kids have referred to them as such. Even when you're not really sure where you're going, what you're doing, if you can write that 12.3 grams H2 right here and give yourself these bars. We know we're making some kind of conversion. Draw our happy face down here. You have a start. It gives you a starting place to go. And then play your same game. Whatever's here goes here. We have grams H2 down there. And now we get out our molar road, see where we're at. I've started with mass, right? So I'm going to need to use the molar mass to get to moles. So I start with mass of our H2. We're going to use the molar mass of that H2 to get to moles of H2. The one rule that does hold true here too is that every single one of your conversion factors is going to have moles in it. It won't always be 1. The only place it won't be 1 is that molar ratio. So I need to find the molar mass of this H2, which I've conveniently calculated for myself earlier. Go 2.01588. Now, why is it 2? The periodic table says it's 1.07. Well, because we're looking at H2 gas. Okay, so this H2 is going to have twice the molar mass of that the periodic table says is equal to 1 mole. 1 mole of this substance will equal this mass. Okay, but we're not there yet, right? Because I need to get to mass of O2. So now I'm on my molar road here, and I need to get to moles of something else, which is something that we've already done. So we're going to go through this molar ratio. Last time we talked about how we use the formula, because we were always going to moles of like atoms or moles of chlorine in sodium chloride, but now we're going from hydrogen to oxygen, something completely different. We use the molar ratio. Okay, the molar ratio comes from a balanced chemical reaction. Balanced chemical reaction. Molar ratio comes from a balanced chemical reaction. You know how sometimes in class I repeat the same thing over and over and over and over? It's because it's really, really, really important. Molar ratio comes from a balanced chemical reaction. So our next step, we take our moles and we drop them to the bottom. Moles H2. And we're trying to get from our molar road to molar avenue, we're going to go to moles of O2. Balanced chemical reaction. So we come back up here, moles of H2, there are 2. Moles of O2, there's 1. Okay, but we're not there yet because we're still looking for mass of O2. Whatever's here goes here. You want moles O2 down here. Okay, and then where we're trying to get, once again, now we're on molar avenue, and we're trying to get up to mass of that. So we're going to go through our molar mass one more time. Molar mass of O2 this time, right? So we want grams up here, is 15, nope, sorry about that, 31.998 grams, oops, O2. So you guys know how in the last chapter I emphasized writing the compound, writing the substance after everything? This is why. My grams of H2 are going to cancel with grams of H2, and my moles of H2 are going to cancel with my moles of H2, but these two moles are completely different things. So this is going to cancel. This is a 1. The only time you will not have a 1 in front of your moles is right here in front of this molar ratio. This cancels with that, and I am left with grams of O2, slightly messy because I started to write the wrong number. Okay, and it suddenly occurs to me that I don't have a calculator, so we're going to estimate. Oh, this is approximately 32. Divided by 4 should be 8. So 12 times 8 is going to be like 96. So it's going to be like 98.38, I'm guessing. You guys try it in your calculators. Grams O2. Right? Is no different than what we were doing before, except for the single addition of this one conversion factor right here. Okay, I'm going to work another one. I want to work one now with volume. Okay, if, let's say, actually we'll work with volume and particles. If I need 2.38 times 10 to the 23rd molecules of water, what volume hydrogen at STP will I need? Question mark. Okay. Same process that we have always used. Start with your number, 2.38 times 10 to the 23rd molecules of water with our smiley face. Okay. What conversion factor? We've got molecules here. Sorry, start there. Molecules here, molecules here. We are always going to moles. Okay, this is just like we've always done. We have to get to moles of this same substance first before we can change substances. What are the numbers? 1 mole, because it's not a molar ratio. And then how many molecules? Right? 1 mole is 6.02 times 10 to the 23rd. Okay. Now I bring this down again. And we're going to change substances. So we're going to go from moles of water to moles. I was asked for hydrogen this time. Okay. Where do those numbers come from? Again, our balanced chemical reaction. So we have 2 moles of water, 2 moles of hydrogen. I know they reduce. Humor me and write the numbers in anyway. 2 moles of water, 2 moles of hydrogen. Okay. And now to finish it up, what was I asked for? Well, I'm asked for a volume. I bring my moles down. Moles, hydrogen, and then I'm going to go to volume of a gas. So that's liters H2. And again, we ignore the STP. All it tells us is that this number right here is 22.4. Okay. And then you do some math, and honestly, I have absolutely no idea how this is going to come out. Oh, we can estimate this again. It's going to come out to about, let's see, a little more than a third of 22.4. So it's going to be like 8 liters H2 or so. If you get 7 or 9 or something close to those, it should be pretty close. Okay, so I've got a worksheet in the classroom now. I put in the answer key. I encourage you to do the problems and then look at the answer key and not automatically go to the answer key to do the problems. Make yourself do it. Okay. Wish you best of luck. Let me know if you need anything. Okay, I'll be available if you need me. So good luck.